I'm Justin, CTO and co-founder of Althea. And today I'm going to be talking about building an ISP in a box, or sort of a new economic model for last mile networks. But before I go there, I'm going to take a brief detour for those of you who aren't already familiar with sort of the economics of building last mile networks, and explain a little bit about what it costs and what the barriers are. Particularly from my perspective, since I'm most familiar with wireless ISP equipment. But the long story short is that you can hook up a customer with better than median US internet speeds for $300, and that's a pretty conservative estimate. The numbers change, the exact details change. Maybe you go with fiber, maybe you go with cable. But no matter how you do it, building infrastructure is wildly profitable, and coordinating it is what is hard. The actual hardware cost is really pitiful compared to the cost of building the actual network out. Now, I'll take a moment to say that last mile networks are by definition within a few miles, somewhere less than 50, of existing fiber backbone infrastructure. You have end user homes or locations that just don't have access to good existing infrastructure. And when you ask why that is, people often say it's just expensive. Well, it's not expensive to build, it's expensive to coordinate. It's expensive to gain access to customer property to install equipment. It's expensive to gain access to business property or city property to build the infrastructure that you need to build and place the rather cheap equipment in the correct locations. So how can we solve this problem? How can we increase the availability and reduce the price of internet access? And we actually have a very successful model for solving this problem. It's called the internet, and it's where a group of autonomous organizations cooperate to form a network with no single owner, and this creates better efficiency. If one company wanted to own the entire internet, it would not be feasible. They simply wouldn't be able to coordinate it because human communication does not scale that well. On the other hand, automated cooperation and human cooperation in the form of events like NANOG and other peering groups really are what make the internet cost feasible in the first place. So what if we could apply that same principle to the last mile? Because right now, the only way you can make money as an ISP, as a last mile end user ISP, is to have subscribers, so fully captured subscribers that pay you for temporary access to your monopoly on infrastructure to their location. And this is great if you're a provider. It's a very steady stream of income. It's very predictable, but it's not so great if you're a customer who cannot share resources, cannot make use of multiple pieces of infrastructure to their home. And more importantly, you end up with really ridiculous situations where one home has good internet access and maybe 200 feet down the road or a mile down the road, somebody has horrible internet access. And they ask, well, why can't you just hook them up? It seems easy. And that's because it is. The $200,000 or $2 million or whatever ridiculous number you hear when you hear this anecdote is the price you are paying for the monopoly ownership model of existing ISPs. So this is what Althea is. It's a system to change the economic model of last mile ISPs by sort of shrinking down and automating the internet's peering model where many different people participate in a single network independently, and compensation is moved through the system through peering agreements, or not necessarily peering agreements, but transit agreements. Forgive me if my terminology is a little off here, because I'm trying to apply concepts from the larger internet to a smaller automated scale. So I'm sure we can have arguments about semantics all day if somebody felt like doing that. So yeah, the principle is that we can reduce cost and increase access by allowing people to cooperate on the last mile. But how do we do that? Can we really automate that effectively? Yeah, so how we do this is that we're not proposing something like a new internet or something strange. What we are proposing is essentially a normal last mile ISP in all appearances on the outside using perhaps point-to-point wireless, fiber, or cable. but each user is capable of selecting their own routes, providing transit for others, being paid and paying for these services completely automatically. And from the perspective of the outside world, you could say that it's just a bunch of Wi-Fi routers paying each other for bandwidth. So can we implement this? This is something right out of science fiction. And the answer is yes, we can. And in fact, I hope that by the end of this presentation, you'll believe that it's very simple. My goal is not to convince you that this new economic model is the best thing since sliced bread. It's to convince you that it can at least be built, and it is possible for it to be competitive with existing systems. And in fact, we have already built this. You can download it and use it. It's open source, github.com, Althea-mesh. Now with the explanation sort of out of the way, we can get into the technical details. So what we ended up choosing as our platform is OpenWRT routers, which is sort of an odd choice from the perspective of how to build a new system, but it's a very effective choice in terms of reducing costs and making it easier to get stuff into customers' homes, because primarily we need agency. The customer needs the the system that is in the customer's home needs agency to make routing decisions on their behalf, to pay for routes and bandwidth, and to generally do the buy side of this autonomous bandwidth market we're talking about building. And within that footprint of an OpenWRT router, we have to fit everything that you would traditionally have an ISP do. So this is QoS, routing, even stuff like incident resolution, and of course our headliner feature, peer-to-peer autonomous bandwidth payments. Yeah, so here's a network diagram. I'm not going to go over this in detail, but I want to call a few things to your attention, other than the fact that the NAT isn't there when people are using IPv6 native. Mainly that traffic goes through an arbitrary number of routers, and these can be any particular hardware device, before it reaches an exit. And an exit acts as an interface between the Althea sort of peering system and the traditional internet. It's also a trusted endpoint for user traffic, because we have a situation where the user's router may decide, hey, you know, that connection over there is a little bit cheaper and its latency is a little lower, let's just switch the traffic over there. So obviously we need some encryption. We also have a second problem in that we need to bill everyone along the route appropriately. So we need to account for how much traffic they have transited, because because payment is made per byte of traffic forwarded, and I'll get into the details of that later. So we have a second layer of encryption in between each device that allows us to securely authenticate each payment. This way you can't simply change the packet headers and have somebody else pay for your DDoS attack or whatever malicious behavior you're trying to perform. Now, I know what you're probably thinking. We are doing 2 layers of VPN encryption on an embedded device, and the great thing about the OpenWRT routers is that they let us play man in the middle for everybody's smart fridge, so we don't have to write any special code for that. The bad thing is that we have to run all of our code on, to be generous, serial box processors. But that's actually not nearly as bad of a situation as it was just a few years ago. Here I have some kernel flame graphs of packets being forwarded. And I think the software for this is by Brendan Gregg. Did I get the name right? But anyways, the key thing here is that since the advent of smartphones, ARM has become more and more popular as a router CPU choice. Previously it was MIPS, which is exceptionally low cost, exceptionally simple, very good at what it does, but rather slow. You can see the Cha-Cha 20 MIPS category eating up almost half of this packet forwarding process, and then the tiny little candlesticks of the kernel doing its routing job. On the other hand, if we take a look down at the ARM version, you can see that we have a neon vectorized ARM implementation of the encryption, and the entire graph is dominated by the kernel doing memory lookups. This means that we can, on cheap, otherwise low performance devices, achieve, let's see, so for $90 you can get 150 megabits, for $160 you can get 500. If you're willing to go 300, you can get 10 gig. The question is whether or not you're willing to tolerate a fan. So yes, it is in fact possible to perform the encryption and authentication required for a system like this efficiently, even with very cheap devices. You don't really end up adding much, if any, cost over a normal end-user CPE to achieve better than median US internet speeds or much better than median US internet speeds, depending on your target price. So the second bit of this is network engineering. So we're talking about creating a network where people are allowed to connect devices in arbitrary ways and have them pay each other for bandwidth. That hypothetical situation I started out with, where you simply connect a neighbor, that's possible. And in fact, we also have to tolerate the situation of where people may connect many neighbors in otherwise in the sort of network formats that we wouldn't allow. So as network engineers, what we normally try and do is that we build the network, we lay it out, we architect it to not be overloaded from the beginning. But we really don't have that luxury if we're going to go for this distributed system. So how do we solve the traffic management problem? And people on our team actually make fun of me for being a CODL evangelist, but it really is that good. What CODL, or FlowQ CODL specifically, is a traffic management system that hashes the headers of packet streams in order to on-queue each packet into a queue for its specific connection. So you have many different queues, and they are dequeued, smallest queue first. Now this is a gross oversimplification, and I might even get an email from David about summarizing his system wrong. But the long story short is that this is an automated, fair bandwidth allocation system that prioritizes low latency. Meaning that if you have a big downloader on the network, the lower latency traffic goes first, the higher latency traffic goes second, seamlessly. And you can achieve really great performance in very crowded networks. This is a benchmark taken from bufferbloat.net, which you should all visit. And it shows that in exchange for a 2 megabit per second reduction in average throughput, you can receive a 17x reduction in average latency. And these benchmarks are entirely borne out by what we actually see in the real world. In fact, I would say that if you are providing connections to end users and you are not performing some sort of CODL flow control, you are doing them a disservice. This solves the problem of limited connections getting bogged down, latency increasing, bad user experience. It's not something that has to happen anymore. It's just a TC module that's in the kernel, it's open source, feel free to use it. It is really just that great. And I strongly suggest you try it for yourself. So for us particularly, this is deeply important because we have to deal with arbitrary architectures. So it handles the fair sharing problem. We apply 2 layers of CODL, you might have noticed in our earlier diagram, and that essentially allows us to fairly share bandwidth between routers, so different homes, and then share bandwidth on a larger network scale where many routers may be going through a single point in the network, and in fact new connections may be load balanced to or away from any given link at any given time. So yeah, now we're going to get into sort of the fun stuff, the routing, mainly how do we automate the BGP in this mini internet sort of model. So we use Babel, which is an open source distance vector link state detecting routing protocol. It's pretty exhaustively defined as far as specification. It's an IETF spec, and it provides extensibility. And also important for us is that it inserts routes directly as kernel routes, since we get most of our performance from allowing the kernel to handle packet forwarding. So what we have done is that we extended Babel to have multiple distance vectors. So this is the sell side of our autonomous bandwidth market. And instead of trying to come up with some sort of negotiation process where the buyer has to negotiate with the seller, the process of advertising a price in a sale is simply a distance vector operation. So this is well understood, well known, and very doable. What we have done is bring in multiple distance vectors. So price is just hop count where you pick your own number. And we also have 2 other vectors, round trip time and full path packet loss. And these are important because you need to not only evaluate the price of a connection, but also its quality. And the methods you use to validate the quality of a connection need to be verifiable because, as you probably know from news headlines, BGP and existing distance vector routing protocols do not prevent metric spoofing. So if we're going to create even a much smaller scale network, we need some way to prevent spoofing if we're going to confidently say that this can be automated. So from earlier in our presentation, we had a encrypted connection to an endpoint called the exit that peers out our traffic to the existing internet from the Althea system. And we have an encrypted connection that we can tunnel verification of these verifiable metrics over. So we can determine the round trip time and the packet loss to the exit, which is advertising the route to us, and compare it to the actual values that we have, to the advertised values and to the actual values, depending on which direction you're doing that comparison in. And then we can apply these changes to our routing table and fully understand, compensate for whatever fraud is going on, or perhaps even just accidental inaccuracy. So here's an example of a network with the three different metrics in action. One of these is best price, one is best round trip time, and one is best packet loss, but I've forgotten which. So now, for actual routing decisions, we re-aggregate these metrics as the sum of the logs of the values multiplied by a scaling factor that allows the user to have some selection over whether or not they want a lower price connection or maybe a certain mix of price and latency. But the exact outcome is not exactly fully user selectable because we are not using any of Babel's source routing features. So the kernel rules inserted only allow one route at a time, meaning that your packets will follow each individual node's preferences as they traverse the network. So that's an easy opportunity for improvement in the future, but not something we've really bothered with so far. Also, the other thing to note here is that this is a linearly scaling memory usage routing protocol, like all distance vector protocols that I know of. So this means that we have a limited number of routes we can have in the network, and we have to deal with potential scaling problems that may reveal themselves as things grow larger. But that's really not the most difficult challenge as far as dealing with automated routing. You can get up to 4,000 nodes with the default settings, and the overhead is very reasonable, and at that point you can subnet. Users are not going to be happy with their internet experience if they're going over more than 5 or 6 hops to get to an exit anyways. So you're not really going to encounter that. And if you did, there are definitely some optimization opportunities in Babel. I think we can at least get it to 10K and maybe 100K without changing the hardware or meaningfully needing faster devices. Now, the real challenge is that there's a fundamental limit to how accurate metric verification can be, because Babel is advertising these routes out of band in user space. So when you receive a route from Babel and it says that this has a packet loss of 3%, you're actually seeing a sample over the default update rate times the number of hops. So like 4 seconds is the default update rate, 4 hops would be it's a 16-second sample. So when you perform your verification with the exit, it's going to be an almost instantaneous operation. And you're going to have to reconcile essentially those two probability distributions. And this is the one thing in this presentation that we do not actually have in production yet. We have the full path route. We have price determination. We have the full path route quality and round trip time and latency all sort of working, but we do not have the automated verification on and in a state where it will actually do something about potential fraud. That's because we've spent about roughly 6 months on each component, starting with the original Babel and WireGuard set up, about 6 months to get the network component of that stable. And then we've just sort of wrapped up billing and getting billing to really work. And what I really mean by billing are bandwidth payments, because there's a lot of things in this system that you could qualify as billing. How we do this is device-to-device cryptocurrency micropayments. So what the user does is that they simply deposit money into their router, and their router will pay everyone along the path. And in fact, it's very important that we have access to an API that's a lot like cryptocurrency. We don't really need a blockchain so much as we need digital money, well, digital cash, where the device itself can hold funds and can pay adjacent devices in very small amounts. So our average payment amount is 10 cents. Because the key insight that makes the buy side of our distributed bandwidth market possible is to simply unwind that distance vector price network. So if I have a route and this route says that it costs 10 whatevers, I will pay a lump sum to the first node, who will then pay the next node out of that amount. And by keeping the payment amounts very small, like I was saying, 10 cents, the most a hostile node could walk off with at any given time is a dime. If it costs them $5 to register their identity, then it's never a good deal for them to steal your bandwidth payment, because they would then be found to be fraudulent, and that would end quite badly. Yeah, so this brings us to the more complicated problem on the buy side of our system. And that is that we need to be able to deal with faults. Particularly packet loss happens, packets get lost, packets get retried. All sorts of different problems occur. And we really don't want to come up with a very chatty Byzantine fault-tolerant system for determining whether or not a payment was actually made, how much was owed, and things like that. Like I was talking about earlier, we advertise prices using distance vector, and this makes the whole system very efficient because it's exactly the same sort of route advertisement you would see in a distance vector protocol. There's no additional back and forth overhead to deal with the pricing structure. So how do we achieve payment with an equally small amount of chattiness? And the answer to that is pay per forward. So in this model, each node is paid per packet it forwards. Loss and other disruptions simply resolve to an overpayment. So node A would look at its TX counter, determine how much it was supposed to pay, because it has the advertised price to multiply by the TX bytes. And the receiving node would take a look at its RX counter and multiply that by its advertised price to come to a decision on what the other user owes them. In the case that some packet loss has occurred, the TX is slightly greater than the RX counter, and the second node simply believes that it was slightly overpaid. And this is great because it prevents us from needing very complex dispute resolution systems and resolves all communication about how these payments are performed to a very simple advertisement, which is part of the distance vector system in the first place, and then a payment message. You say, hey, I paid you, and there's no negotiation over what the amount should be or how much was sent, or really anything that you would have to get into an exceptionally complicated adversarial communication protocol to deal with. So here is a payment map from our production network over 1 week. It's interactive. You can visit that link and play around with it. Anybody who has been thinking about what I've been talking about has probably realized that on a real last mile network, almost all the traffic is download traffic. So how does pay per forward work? And the answer is that exit nodes are actually the exception to the pay per forward model. We simplify the complicated general case in which we may need to pay arbitrary nodes over arbitrary path at an arbitrary period of time into pay per forward, which is very resilient to problems. But the relationship between the exit node and a client, which is just a two-party relationship, involves the client paying the exit for download traffic, which is slightly more trustful because you have to trust what the exit says within reason on things like packet loss. But it greatly simplifies the general case, which is what we're really looking for here, and that's what has allowed us to get a working system implemented in a reasonable amount of time. So yeah, payments are out there in the real world. They work. They're pretty stable at this point, although I'll talk about some of the problems we've had developing it later if I end up having time. Yeah, so some of the fundamental challenges with billing is that we're committing a cardinal sin of being both a network protocol and a network application. So most of the time you have a network protocol and it is completely separate from any network application because the job of the protocol is to stand the network up. But in this case we have a network protocol that depends on the network working in order to reach the outside world to pay people for bandwidth. So this is a bootstrapping problem that we had to come to a robust solution for. And what we do right now is that we provide a little under a megabit of bandwidth that is free, not necessarily free so much as never turned off. So users who do not pay are never completely cut off. They have enough bandwidth to reach out into the world and make a payment to get themselves back online. Most of our bugs or errors involving payment after a painful several-month period where we had to figure out all of the different error cases you can have when you're both standing up the network and trying to send a packet out to the internet, are related to the unreliability of the blockchain as far as getting payments in. There's a fairly complicated process on that end as well, so we've had to integrate some more logic into our system to compensate for issues there. Finally, you can have devices that just get a bit flipped by a cosmic ray. It does happen. They don't have ECC. They do need to be rebooted. You know, it's hard to isolate these sorts of problems from just random errors in your application, but I've had a few situations where the outcome was just so ridiculous that I had to believe that the device was corrupted in some way. But in general, we can handle those pretty well now after I've seen a few of them. So yeah, looks like I've got about 2 minutes to tell some stories about building a system like this. So we have a test network of about 50 customers. This map is sort of old, in Clatskanie, Oregon. And on average, the downtime is about 15 minutes a week, including patching cycles, which is not all that great, but it is mostly skewed by finding bugs, which is exactly what you want in a testing network, to be big enough to find bugs, but small enough that you're not going to inconvenience too many people while you do. Now, that is average across the whole network. So, for example, if we have one user down for an hour, that would skew the entire network average for a while. So we have included automated incident recovery, which I talked about in the first slide, but I didn't end up going into detail there because I've essentially automated hitting it until it works again, and I found that works out very well when necessary. The speed and latency at 2 or even 3 hops into the system is still 100 megabits per second, about 10 milliseconds to get all the way out to the data center. I measure this by pinging Cloudflare because they have a server in PDX where we locate our exit and peer out to the outside world. We do perform automated patching on these devices, so the general advice is that you should not update OpenWRT devices on a script. But we have, and we've done so for the most part very successfully. We had one failure where the update disabled the update system, but the network was still working, so we were able to sort of sneak around and get that all fixed without anything too disastrous happening. Generally, users are pretty satisfied. This is a rural area. Most of these users are coming off of either 2 generations ago of fixed wireless, where they have less than 5 megabits, or DSL, where they also have less than 5 megabits, or cable, which is so oversold that they can't maintain a good video call because packets get dropped all the time. So it's really not exceptionally hard to do better than what's already provided in rural America. And in fact, many urban areas as well still have only DSL as an option, simply because nobody can coordinate installing new infrastructure into the area. Pay-per-byte billing is definitely it's both an advantage and a problem. There are lots of people who like it because it is better for the consumer in situations, well, for most consumers actually, because almost all almost all ISPs today sell you a connection with a cap. And when you do the math, that's really just selling bandwidth for 7 or so cents a gigabyte, with no option for a refund and no option to pay less if you use less. For most people, Althea is a better deal because it is being done, well, because they receive the discount if they end up using less or if they're out of the house or whatever. It does have downsides, and mostly in that users are sort of uncertain about the nature of the new billing method, and they want some level of understanding of what's going on. We've added some new features recently that show the user their average usage, the expected time left on the money they have deposited in the router, and that's gotten really positive responses. Yeah, I think I'm pretty much out of time here, so I'll go ahead and take questions. How far ahead are we? I have 5 minutes left? Oh, wow. You know, I tested this and it always came out to exactly 30 minutes, but I guess I got a couple of minutes on the start. And I sabotaged my own strategy of going so long that nobody could ask me questions.
Hello, Tim Novacek, All Points Broadband. Are you mostly using 5 gigahertz or are you investigating using 60 gigahertz for your microwave?
Okay, yeah, so I did forget to mention this. We're completely medium agnostic, but we mostly use 5 gigahertz in our test network because it's cheap and fairly performant. As you can probably tell it's 5 gigahertz by the performance numbers. We are standing up a 60 gigahertz link to one of our relays, which is a customer that serves other customers because they provide a tower, they receive a cut of traffic that transits their node. And the idea there is that we're going to actually plug 2 antennas in parallel into the system and do a sort of 60 gigahertz to 5 gigahertz failover, but using Babel and its link state detection rather than some of the integrated systems that Ubiquiti and such are talking about offering in a year or so, I think.
And CBRS, is that on the way as well?
CBRS, I'm sorry, I'm not familiar with the acronym.
265 to 2, or 26 to 2, or sorry, 36 to 38 gigahertz, the new open spectrum that.
Yeah. Once we can start to get our hands on that, sure. But right now, we don't look too far forward as far as what the connection medium is, because for the most part, what's available performs really well. You know, MikroTik has those wireless wires, which for about $300 will do gigabit over a little over a mile. So we can't really complain about the cost of hardware.
Thanks.
Leslie Daigle, Thinking Cat Enterprises. Thinking Cat Enterprises World HQ might in fact be located in an environment that doesn't look very dissimilar to your pictures with the possible addition of mountains. I wanted to know how many deployments do you have? Do you just have like the one test one, or how many different deployments do you have?
Yeah, so like I said, we just recently got billing into a state where we felt comfortable with it. So right now we have 2 sort of in production deployments with billing running and that sort of stuff. One in Clatskanie, Oregon, one in Medellin, Colombia. And they're both running and working okay. And now we're into sort of the sales side where we're trying to start up a few more deployments, and they're in the process of signing up users. In fact, if you visit altheamesh.com, you will find our sign up process going on there as we try and stand up another, I've lost count, deployments, but I think it's really like 4 or 5 we're focused on right now.
Right. So your model is basically you will take on these on by case basis and work with the environment to build out the mesh. I mean, my question really is, you mentioned that you're hardware agnostic, which is good. I mentioned that there are hills, which is not so good. We kind of run into the line of sight is challenged.
Yes, so this is actually one of our big selling points, and that's what I was talking about when I was talking about cooperation. So if you take a look at our network diagram here, This isn't like a so this isn't a map that shows elevation, but the position downtown where we have our fiber drop to, in as much as anywhere is downtown in Kletsknai, is not the sort of position you could build a traditional WISP out of. It doesn't have great lines of sight. You couldn't see enough customers from there. But you'll notice that we have relays. This map is old. There are more now. But these are people we bounce the signal to and then bounce signals from to other users. And this is sort of the reason that we believe Althea has advantages, because these users, we didn't have to access easements or anything. We came to them and we're like, hey, we're going to help you install a pole onto your property, and it's going to provide service to other people. You're going to get paid for it. Now their internet bill is 0 or negative in the case of some of our relays, and they're extremely happy with the whole situation.
Great. So if I can catch you in the break, we can then talk about trees and other little impediments.
Yes. I'm afraid they're coming up here with the hook, so I'm going to go ahead and let the next presenter go. You can catch me outside for more questions.